Hello, my name is Warren DeWitt from Radiance Technologies, here to present a social influencer model for neurostimulation mapping, our submission for the xTechBOLT semifinal competition. So before I get into the weeds of what I propose to do, I wanted to talk for a moment about who I am and who we represent as a company. I work for Radiance Technologies, which is employee-owned and a small business, but in many ways a traditional DoD contractor. We work with DARPA, NASIC, NASA, the Army, Navy, Air Force, and just about any other government agency that needs something done. However, we have some pointedly non-traditional pieces in that we maintain two internal structures. The Technical Fellows, which is an internal research and development organization that tries to maintain some academic reach back, participate in conferences, publish papers, and just generally push our envelope of technological offerings. As well, we've recently piloted the AI/ML Innovation Cell, which, while machine learning is a pretty core part of what we do at the company, we're trying to reach new avenues with how we use it and find some very novel applications. So at the center of these is myself, the principal investigator for this project. I'm the head of the Innovation Cell and one of the technical fellows, but as well, I'm actually studying intent-driven EEG for control of semi-autonomous systems for my PhD in computer science at the University of Alabama, Huntsville, with part of the Big Data Laboratory. So when xTechBOLT crossed my desk, we were immediately excited because it kind of hit all three different hats that I wear at the company. So my team mostly consists of myself plus a group of physicists and machine learning engineers in the Innovation Cell, the scientists from the Fellows group, and then I have the academic side through the University of Alabama, Huntsville. So now that we've talked about why we were interested in this, I want to jump into my concept for how we think we can increase learning outcomes. So I see it as you have a training exercise and you're applying biofeedback to try to make that more effective, what I call the training acceleration loop. And what I want to do is apply neurostimulus so that the learning actually happens at a faster rate inside the brain. So this loop has several pieces. You're performing the task that's undergoing whatever training exercise is happening at the time, and then I want some kind of headgear to recognize when learning is taking place on a microsecond level, predict what regions of the brain are going to be affected, and then apply the stimulus to those regions so that they do so more effectively. We can do this, I hope, in near real time with the proper equipment and algorithms. So before I dive into the details on that, I want to say that this has some academic backing. The government has in fact even worked in this area before in a collaboration with Halo Neuroscience, who pitched the Halo Sport 2, one of their off-the-shelf headsets that's meant to increase learning on tasks like playing an instrument. And this has been partnered with by DIU, the Defense Innovation Unit. As well, at around that same time, published in Frontiers in Neuroscience was an application of transcranial direct current stimulation to a very military-oriented task that was piloting and I even believe landing an aircraft, in which they showed that different ways of modulating the neural activity using TDCS had a great effect on the outcome of practicing this task. However, my problem with a lot of these approaches is that many, not all that I see, focus on things like periodic stimulation or constant stimulation or some other less targeted, even if they're targeting a particular part of the brain, not necessarily targeting a particular moment in time to apply that stimulation. So there's the famous myth that we use 10% of our brains, and I once saw on Reddit someone saying, well, that's kind of like saying you only use 30% of the stoplight. If you used all the lights on at once, that's the brain equivalent of having a seizure. So what you really need to be doing is making that one bulb that's lighting up on your stoplight light up slightly brighter at the right moment. That's how you get a more effective stoplight. And as crude as a metaphor as it is, I think that's how you can get a more effective learning outcome in the brain. So to get more into the details, how do we do that? How do we know? And where do we apply the stimulus? And that's my concept of operations too. I want to do that stimulation on demand by building first a real-time learning detector, and then if we can partner with the neurostimulation provider, making an informed learning stimulator. And I propose that we use two complementary technologies, EEG to detect the electrical current, and then FNIRS to get the locations in the brain where the activity is taking place. To me, those are the content and the carrier, respectively. And so if in your training exercise you're wearing a cap that can at the very least do these two things and ideally also apply the stimulation, then off of the EEG signal, I'm looking for a particular trigger so that I can run it through my stimulus map and say, okay, when I see that trigger that indicates learning is about to take place or is on the onset of taking place, I can predict that a pathway of activation will happen from, say, here to here. That way I can apply stimulus to both endpoints and even all along the way of that pathway and hopefully make that learning outcome more effective in the cap. And we can just do this on a microsecond scale in real time. And that way the EEG provides my trigger, that's this, and the FNIRS is my target. So this is already taken care of by an off-the-shelf EEG FNIRS headset from xTech. This much we can do using deep learning models like neural nets to perform the classification. The question, the stimulus is something that I think we need a partner for. So I'm mostly pitching getting us to here, but we'll talk about that on the delivery slide. So the question is, how do I go from the trigger to the stimulus map? And that is where I want to introduce something novel. To me, the brain is very much a network, and I think we can apply social network analysis. This is a visualization using a radial dendrogram, or a chord chart, whatever you want to call it, of brain region connectivity, and this is some blogger's group of Facebook friends, just the immediate friend. But when you look at them, where you have strong local regions plus a few that reach all the way across, they're not totally dissimilar. And I think that the pattern of locality between the two and the way that information flows is worth exploring. What's really fun about this, though, is that if our goal is to try to find what region is going to be most effective at promoting learning, that's almost the exact same problem that organizations in advertising or politics want to do when they target the influencers. And algorithms like that are very well documented in literature and used by companies all over the world today to great effect. I vote that we treat the brain like a social network and try to, on a particular trigger, EEG topic, whatever you want to call it, actually identify which regions of the brain are the influencers that need to be accelerated as a result. So now that we have that pitch, let me go into some of the more programmatic details of how we would actually get there. I think we can do this exploration and get to, at the very least, a detector and potentially even the full pipeline in about 18 months, and I'll break those down. First, we need 2 months where we can plan, get the equipment, and do a neurostimulation trade study. If we can find a partner that can provide the neurostimulation, because that's the big gap in my company, we can get you the detector. Then I think we can go and produce a biofeedback pipeline as a result that will actually apply that stimulation. However, either way we can get a fieldable system, because even if we don't get it all the way to the stimulating step, I think we can still yield a wearable detector that will tell you where and when you should apply stimulation and write an ICD so that you could attach it on in a future project. So how to get us there? First, we'll do a trade study on neurostimulation providers, get the equipment in, and then work with the Army to coordinate when we can actually do the data collection. So I've allocated about 3 months for us to put the caps into rigs, and that's pretty simple because xTech has some excellent units off the shelf. And then actually put these on some of your soldiers during the training exercises and just record data. It should be the same exercise. We'll just be making a data set as it happens. Then we'll take that back and spend about 6 months performing this analysis. So there are 3 steps to that. First is figuring out the pathways of flows, that's the FNIRS. Then we do a classification exercise for the EEG, and then we use the social network analysis to link the two together and build what I'm calling the stimulus map. Once we've done that, then it becomes more of an integration exercise, just some simple hardware, software, firmware, where we build the detector, install it on some kind of mobile board like a Jetson or a small FPGA, some other board that we think we can easily field. And if we have that neurostimulation provider, connect it, otherwise design the interface so that you can plug one in. Finally, either way, we can package it up, run through all of the procedures we need to get it into the hands of the US Army. So some of the tools that we'll need to do this, the G Nautilus FNIRS is off the shelf, looks like this. It's already, I believe they have a wireless version, it's very portable, and it kind of comes with everything you need out of the box. Then for the actual AI training, I think we can use some Lambda workstation or equivalent to perform the analysis on. As for making the fielded detector, NVIDIA Jetson has these mobile GPUs that are excellent for deep learning, and they're tiny, next to a little Lego figure here. So really the only risk item there is whether or not we can get a neurostimulus item, but we can get to a deliverable product either way. I've put a ROM cost of this at around $962K, and that will allow us to do data collect on 5 different individuals. Finally, just talking about where we might go in the future, I think this idea could be extended. The Neurable has already demonstrated a very nice integration of an EEG with a VR headset, and VR is already being shown to be very effective in medical training. Secondly, I think that streamlined integration will work. We're all used to EEGs being these gangly things, but slowly people are finding which are the most effective channels and producing much more streamlined headsets that would allow you to use it in more extreme training environments. The micro-targeted stimulus, this goes back to, can we find a neurostimulation provider? There's already been reports that are trying to forecast how those are going to come down the pipe in the 2020 to 2030 decade. And I think we can piggyback on a lot of that new market in this project. And then finally, haptic feedback will increase the training outcomes and could tap in as another input to our biosensing pipeline. So finally, these are my references. You can find additional ones in the white paper as submitted. And thank you very much for your time.